the last lecture we have seen definitions and some basic properties of the integral extensions. Today first we will see some examples, and then we will continue the connections with the prime spectrums of extensions of rings. Alright, so let us see some examples. Alright, so one, let f be a monic polynomial of degree d with coefficients in a ring A. This is a monic polynomial with coefficients in the ring A, and as usual A is our base ring, commutative. I will not write, I will just say A is a ring. So this is a monic polynomial of degree d. Degree f is d and f is monic. And then consider the residue class A algebra polynomial ring B, let us call it B, which is polynomial ring modulo the ideal generated by f, and I will denote X to be the residue class of X modulo the ideal generated by f. That is the notation. So this is also equal to Ax. So it is obvious that this is a finite type algebra, but we will prove more. So then B is a finite A algebra in fact B is generated as a module by 1 x etc. A up to x power d minus 1, and in fact B is a free A algebra of rank D with A basis 1 x etc. up to x power d minus 1. All these things one can check easily by using division with remainder. So I will just write here division with remainder. That is possible for arbitrary base ring A provided the polynomial was monic. So this we can use it since f is monic. So in particular the ring extension from A to the inclusion map to B, this is via polynomial algebra. So this one is an integral extension. When we say a ring extension is integral extension, that means every element of B is integral over A. That is, it satisfies the polynomial over A, monic polynomial over A. Alright, so second one, this is very important concept of normalization. and this is more in geometric in nature, but to see that we will have to work it more with the language. If in this course I think we will not have enough time to go on to this geometry part, but this is done in my existing course on commutative algebra on which is already on NPTEL 2019 January. Alright, so let A be a ring, base ring, and let QTA, this is S naught inverse A, be the total quotient ring of A. That means, so this S naught you take maximum possible multiplicatively closed set so that this ring does not become 0. So, they take S naught to be equal to the set of all non-zero divisors, the set of all non-zero divisors in the ring A, and you invert them all, the localization. So, therefore, we have this iota map from A to S naught inverse A. This is an injective ring homomorphism. This we have done this while we were studying localization and so on. So, the integral closure, in the last lecture we saw the integral closure of a base ring in a bigger ring is the set of all integral elements over the base ring, that is called the integral closure of A in I will keep using the notation QTA is denoted by A bar and is called the normalization of it. We say that A is normal or sometimes also people use the word integrally close. And when you do not write where, that means it is understood that it is in the total quotient ring of A. Integrally close if A equal to A bar, then you call it integrally close. Alright. One more comment I want to make. If A is a domain, then one call it a normal domain. That is not the comment I want to make. I want to make more serious comment. The normalization, that is this A bar, the normalization A bar of A and I assume here A is an integral domain. If A is an integral domain, this QT of A is the total quotient ring is in fact the quotient field. Of A is the smallest subring of QTA which is normal, and it contains A. So, so look here, A is here, QTA is here, this is the quotient field of this ring A, and A bar is the integral closure of A in QTA. Obviously A contains, A is contained in A bar, and this is by definition is contained in QTA. There is no other subring here which is normal and contains A. That is what this statement means, and I want you to check this. This is not so difficult to, one should check this. So that means take a subring which contains A, then it should, if it is normal and contains A, then it should contain this A bar. That is what one needs to prove. Alright, so I should give you some examples of normal rings or normal domains. Normal study of normal domains is very, very important as far as the algebraic number theory goes and algebraic geometry also goes. These rings play a very, very important role in both the subjects. So I should give some more examples. So third, this is the statement is this is a class of examples which are normal domains. Every factorial domain let me remind you, when I say factorial domain, that means UFD A is normal. When I say normal, that means it is in the quotient field of that A, and factorial means unique factorization domain. In particular, we have lots of examples of unique factorization domains. In particular, polynomial rings, also the power series rings. Over the ring of integers or a field K are factorial domains. In the notation, so Z polynomial in several variables or power series ring over Z or if we have a field, then this Kx1 to Xn and power series ring over the field in several variables where K is a field. These are factorial domains, and therefore they are normal. That means they are, if we prove this statement, then they are normal. So we have lots of examples. Let me just remind you this, for integers it was proved by Gauss. Of course, the power series case in one variable is easy, but power series case in more variables is more difficult than the polynomial case, more variables. Okay. So for a proof, for the proof of the fact that factorial domains are normal, let me give a proof. For a proof, note that it is very easy. Note that if X belong to the quotient field of A, that is A by B in QTA, A, B are elements in A, B non-zero, and if GCD of A and B is 1, so that is where you are using the fact that A is factorial. This is just a reminder we have used the fact that A is factorial. If A is not a factorial, then GCD doesn't make sense in arbitrary domain. Therefore, this factorial is very important. GCD is 1 and suppose this x is integral over A, that means if x satisfies an integral equation which is a monic equation, but if x is a 0 of a polynomial, I am writing the general fact. So, that will this result will follow from the general fact. If you have a polynomial like this with coefficients in A, and suppose this x is a 0 of this polynomial, this is in Ax, then it is very easy to check. Then I will say check that A must divide the constant term A0 and B must divide the leading coefficient. If you check this, then what happens? X cannot be integral, because if x is integral, then it will be a 0 of a monic polynomial, and then that denominator B will divide 1. But if it divides 1 means it will be a unit, and that means this x will be in A. So, that is how the proof is completed. So, this is a more general proof. Okay. Even more general statement than that I will state it, but I will leave it for you to check more generally. And this statement, if x is a 0 of this polynomial, then the numerator should divide the constant term and denominator should divide n. This fact will use this to prove this. We will again need that A is factorial. This is what we have to remember, and this we have done, I remember we have done in the school days for integers. This was a school result. Alright. So, more generally, more general statement than this what I have stated here is the following. The polynomial Bx minus A is a generator of the kernel of the substitution homomorphism from Ax to Qt, Qta, quotient field of A, and this is x is mapped onto A by B. This is our small x, and this is Ex. And what is the kernel? What we are saying is the kernel of Ex. This is an ideal here, and this kernel is generated by the polynomial Bx minus A. It is the principal ideal. So, obviously this generator, you see, it goes to 0 because x is going to small x, which is A by B, and you cancel it. It is indeed an element in the kernel, but you have to check that all elements in the kernel are precisely the multiples of this polynomial, Ax multiples of this polynomial. And once you check that, then if you remember, this kernel will never contain any monic polynomial unless B is a unit, because any element, any polynomial in the kernel of Ex will be multiple of Bx. So, leading coefficient will always be divisible by B. So, it cannot contain a monic polynomial unless B is a unit, but in that case this x will be in the ring A. Alright. So, this is about the normal factorial domains are normal. We have many examples. Now, the next one is the concept of conductors. This is also very useful concept. but again I cannot do more on these things because our course is nearly coming to end. So let A contained in B be a ring extension. That means A is a subring of B and both rings are commutative, that we are assuming. Then in this case this ideal is very interesting invariant. So CA C B over A, this is a notation. This C is for the conductor and this B over A is for this extension. This is by definition all those elements A in A such that A times B is contained in A. This is an ideal in A, is called the conductor of B over A. It is the largest ideal. It is the largest ideal in A, which is also an ideal in B. Normally the ideals in a subring, they may not be ideals in a bigger ring, but in this case this particular ideal is also, it is the largest ideal in A, which is also an ideal in B. So moreover, see what is the how will it be used, will be clear from next few of my comments. If this C conductor ideal contains a non-zero divisor, A in A, then this B will be contained in A times A inverse. See, because by definition if this A is contained in this conductor ideal, then A times B is contained in A. Therefore, when I multiply by A inverse from this side, and where are we working? When you multiply by A inverse, obviously this we are writing in the total quotient ring. Ring QT of A, which is, we know this is S naught inverse of A, where S naught is a non-zero set of non-zero divisors in A. Therefore, this A is in S naught and therefore this makes sense in the total quotient ring. So moreover, so that means we have embedded this ring in A. So that is A is here contained in B and this B we have embedded in QTA. That is where we have used the fact that A is a non-zero divisor, and moreover it is finite over A, moreover it is, so it means B is, moreover if A is Noetherian, then B is a finite A module. In particular, B is integral over A. So just I want to show you just what did we conclude. We started with an arbitrary ring extension and we concluded that it is integral, but with the assumption that this conductor ideal should contain a non-zero divisor. So that is very important Okay, so when we like normalization, when we the ideal, when I take B equal to the ideal, the conductor ideal, conductor ideal C A bar over A is called simply the conductor ideal of A. Where the where A bar is the integral closure of A in QTA, total quotienting of A. All right, so now how do we test? So some important property of the normal domains I want to write, which is very important property and used quite often. So this is what I will state. Maybe I will leave the proof to the as an exercise. So I will just mention the following important property of a normal domain can be easily proved. Prove this. All right, so what is the property? That I want to write as a proposition. Proposition. This is also very useful. This proposition is also very useful in the especially algebraic number theory. All right, so let A be a normal domain. Remember, normal domain means it's a domain and integral closed in its quotient field with quotient field QTA. If X is an element in QTA, not element in QTA. So if I want to further write something. So let L be a QT algebra, QTA algebra. That means it's an algebra over this. This may not be a field, not necessarily a field. I will indicate here where will be the normal situation where one can apply this. So if an element X in L is integral over A, then the minimal polynomial mu x qt A. This is a monic polynomial with coefficients in QTA where x is a 0, is the degree least polynomial. Then a priori this is a polynomial in QTA. Then the minimal polynomial has coefficients in A. Already it has coefficients in A. Now I will just indicate why this proposition is very important. already proof I have left it for you to check. This is not so difficult, but where will it be used, that I will indicate. Alright, so just 2 minutes and then we will make a break. So here is the ring of integers. So the above proposition is often applied in the following situation. So what is the situation? So Z is a ring of integers here. We know the quotient field is the field of rational functions, and we know this Z is normal. It's a normal domain that we know because it is factorial. Since factorial, this was theorem of Gauss, and then when you take a field extension of any field extension, even finite field extension, such fields are called number fields. Number fields. Alright, so and we have an element x here, and suppose this element x is algebraic over. See, this is particularly in a finite field extension case. Finite field extension case. So suppose this element was algebraic over Q. In particular, that will happen for every element when L is a finite extension of Q. Then it will have a minimal polynomial mu x q. This is a polynomial, monic polynomial with coefficients in qx. The above theorem says this polynomial actually indeed belongs to integer coefficients. This is by proposition. Above proposition. This is very useful fact, and the proof is very simple, and the proposition is also stated in more general case where L may not be a field. L is just simply the algebra over Q, and algebraic element makes sense over an algebra over a field. So this is more general situation. So I will leave it for you to write the proof for a proposition. Probably I will also add in exercises with some hints, and with this I will stop this first half of today's lecture, and we will continue after a break. Thank you very much.